The hope is that we do not have to solve this nonlinear differential equation, right, which can only be done numerically. You understand? So, so what do we do? Well, we know that the output is of this form. So, what do? You go and back substitute this in the original equation and see what we get. So, C times, I am going to use the notation V dot to denote the derivative. So, this is Z times VO1 dot plus Z square VO2 dot plus Z cube VO3 dot, okay, etc., plus G1 times Z times VO1 plus Z square times VO2 plus Z cube times VO3 minus Vi, right, plus G2 times exactly, thank you. So, this is minus Z times Vi. Remember, we are applying an input which is Z times Vi, and so let me copy this. Right. So, this times square plus G3 times cube must be equal to 0. All right. And what comment can we make about Z? Z is an arbitrary number, correct? Z can be 10 power minus 3, Z can be 10 power minus 4, Z can be 10 power minus 2, Z can be 1, right. So, if this equation has to, this differential equation, nonlinear differential equation has to be, if you have to have a solution, then it must be valid for all values of Z, right. So, that basically means that you have something, if I can group all the terms with Z, right, okay, and then I can group all the terms with, let me do that. So, if I can rewrite this equation as, if I group all the terms with Z, what do I get? I get C times V01 dot. What about the Z square term and Z cube term? Will they come in here? So, I am grouping all the terms which have only Z in them. Do you understand? Right. So, so what will happen to these two terms? Will they, are they relevant when we group only the terms with Z together?
Which one, like G's won't become in the G2 and G3 terms, like square and cube are there.
No, you are not understanding what I am saying. What I am asking you is, what I mean, do you understand what we are trying to do?
We are grouping all the terms which have the G.
Which have Z. So, now I am asking you what happens with these two terms. Do we need to worry about them when you are grouping all the terms with Z, or you do not have to worry about them?
No, sir.
You do not have to worry about it. Okay. Right. Okay. So, what terms do we have to worry about in the G1?
G1 V0.
G1 times V0 1.
minus G1
No,
Vi term will be there.
you will have a Vi term, correct. So, basically minus G1 times Vi, right. Do we have to worry about
G2, G3,
G2, the lowest order term in Z is, what will be the lowest degree of Z in the, if I expand out the G2 term,
G square will come.
you will get Z square,
And here G,
and therefore, you know, you basically have, we don't have to worry about any of that stuff, and likewise with G3, right. Then, then let us collect all the Z square terms, correct. How does that look like? So, that is C
V0 2 dash
V0 2 dot, right, plus
G1
G1 times V0 2. Is there anything else we need to worry about? We don't, because everything else is either first order or third order, correct. Okay. Then we come to the G2 terms. What do we see there?
they were like G2, G1, G2 times V0 1 minus Vi
G2 times V0 1 minus Vi
whole square.
the whole square, right. Okay. And the other terms will all have degree which is higher than 2. Do you understand? Right. Okay. All right. Plus Z cube times C V0 dot 3 dot plus G1 times V0 3 plus with G2. Now, we should see if we should expect any third order term. Do we see any third order term needed? Because you have a Z term, a Z square term and a Z cube term. So, basically when you multiply the Z square and the Z cube, you will basically, the Z and the Z square term, you will get a Z cube. So, that is basically 2 G2 times V0 1 minus Vi times V0 2. Okay. All right. Okay, that is not all. We have the G3 term also, plus
G3 V0
G3 times V0 1 minus Vi the whole cube, right. Plus, is there something else? All the other terms will be,
like higher
will have order which is higher, right. Plus, you know, you will have, you know, for each order of Z, you can go on writing this stuff, plus blah 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 must all be equal to 0. Does it make sense? Yeah. Okay. Now, this must be valid for any value of Z. So, if that has to be true, what conclusion can we draw from this?
we can substitute different G values and we can.
Okay. If something into x plus something into x square is equal to 0 for all values of x, what comment can you make about this something and that something?
Must be zeros.
They must be 0, correct. So, if these terms are 0 for all values of z, right, it must therefore follow that this must be 0, this must be 0, this must be 0, and so on. All right. So, now let us see what that means. So, what this means is that C times V 0 1 dot plus G 1 times V 0 1 minus G 1 V I minus V I equal to 0. So, what does this mean? I mean, can you recognize
Linear.
what this is? A
Linear first order difference.
linear differential equation. So, what kind of so you can therefore draw a network which basically satisfies that. What is that network, do you think?
There is like G1 resistance and RC.
Very good. So, basically this is basically the same as our original network,
Output will be V.
except that what is the difference then?
Here output will be V0 1.
The output will be V 0 1, but what is the difference between the original network and this network?
Linear resistor is there.
The resistance is linear, right. So, this basically is nothing but G 1 times V 0 1 minus V I. Okay. So, this is, remember, this is a linear network, linear element. All right. So, is VO1 easy to solve or difficult to solve?
Easy to solve.
Right. So, VO1 is easy to solve because the network is linear, we know what to do. Does that make sense? All right. So, therefore, we know we are now in a position. So, the moment you solve this, you are now in a position, we know that. Now, let us go to the second term, right. So, this is finding V 0 of 1, all right. Remember, what are we trying to find? We are trying to find
Those V01, V02.
yeah, we are trying to find V 0 1, V 0 2, V 0 3, etc. right. So, basically we have found V 0 1, right. Now, how do we find V 0 2? Well, we look at this here. What do we get? Since this is 0, what comment can you make about this differential equation? This is also a differential equation.
If it
Is it linear or non-linear?
is like Vi square,
Which is the known and which is the unknown?
unknown is V02. Sir.
The unknown is V 0 2, right. What about V 0 1?
That is from previous equation we got.
From the previous step, we know V 0 1. So, V 0 1 is known. What about Vi is known or not known?
It is unknown like in
Vi,
like Vi previously known.
what is Vi?
Inputs.
It is the input. So, Vi is known.
Yeah.
Do you understand?
Yeah.
Right. So, what is unknown?
Unknown is V02.
V 0 2. Okay. So, now is this a linear differential equation or a nonlinear differential equation?
It will come linear, so like
It is a linear differential equation, right. And therefore, C V 0 2 dot plus G 1 V 0 2 equals
G2
minus G 2 V 0 1 minus V I the whole square. So, how does this look like?
This is the input is V01 minus Vi whole square.
So, the input is that a current or a voltage?
That is voltage. Signs have to be.
What is this equation, man? Is this a Kirchhoff's current law or a Kirchhoff's voltage law?
That is the current class.
Yeah, so so this term here is going to be
Total term will be current only.
current. Okay, so what is the network? What does this represent? This represents a linear network, correct? So this is the capacitance, right? Okay, and I mean, if this excitation was 0, if the right hand side was not there, what would the network look like?
G1 is the
G1 is the resistance, very good. And where would that go?
V0.
It will go to 0. Does that make sense? Okay. And now what are we adding in addition to, so basically that is saying now, I mean we have this network and we are exciting the capacitor node VO2 with a current which is, it is a known current, which is basically, how much is that current? It is going between ground and this is connected across like this, and this is G2 times V01 minus Vi the whole square. Does it make sense? Right? And is this resistance linear or non-linear?
Linear resistance.
This is also a linear resistor. Right? And this is of course the input, and therefore this is known, and VO1 is known from VO, sorry, this is, we must be written as VO1. That is known from the previous step. All right. So therefore VO1 is known from the previous step. Vi is the known input, and this network is linear. Right. So VO2 is easy to find. Right. So this is step 2, right. So finding V02. All right. Okay. Now we know V01 and V02. So what comment can you make about V03 now? So this differential equation must be 0. Is this a linear differential equation, or is it a nonlinear differential equation?
Linear differential.
It's again a linear differential equation. What is the unknown?
V03 is the unknown.
V03 is the unknown, and all V01 is known from step 1. Vi of course is known. V02 is known from
Step 2.
step 2. V01 is known from step 1. Vi is known, right. So basically we have everything that we need, correct. So what is the network now?
Similar to second linear network, we have to have two
Now,
sources.
very good. So we have a linear network again. Right, and we have this is finding V0 3, and so this is V0 3, this is C, this is G1, and what are we supposed to add? We are supposed to add a current which is, we are supposed to add two currents, one which is minus 2 G2 times V0 1 minus Vi times V0 2. Understand?
Sir, but we are writing the KCL at the output. Current leaving is positive.
C dV dt. This goes to the other side, no?
No, sir, this side we are writing at V03. We are writing the KCL.
Oh, sorry, this must be minus. Yeah, sorry. Correct? All right. And we also need to add another current source, which is G3 times V0 1 minus Vi the whole cube, right. And if you solve this linear network, so V0 1 and V0 2 are known from previous steps, right. Vi is the input, is the known input, and the network is linear. So, therefore, VO3 is easy to find, right. So, like this you can go on. I mean, if we assume that the output can be written in this form, then you can plug this form back into the nonlinear differential equation and go on getting V01, V02, V03 and so on. And once you find all this, the output VO of t is simply nothing but V01 of t plus V02 of t plus V03 of t and so on. Correct? Okay. So, in essence, we have transformed the problem nonlinear differential equation to solution of a linear differential equation with multiple iterations. Right. So, one obvious question that comes up is, why can't I use this for when the nonlinearity becomes strong, right? And what happens when, I mean, this sounds like a nice approach where I am avoiding having to solve a nonlinear differential equation. All that I am doing is solving a linear differential equation multiple times, which is much easier to do. So, the question is, obviously this must break down somewhere, and when the equation, when the nonlinearity is no longer weak, right, and that it turns out that what that means in mathematical terms is that this series will not converge, right. So, it will only converge when the weakly nonlinear condition is met. Fortunately, in circuits a lot of the times you are basically trying to, distortion terms are very small compared to, or are needed to be very small compared to the linear term anyway, right. So, this is a very good way of estimating a quick way of estimating distortion and understanding where distortion is coming from and so on. And as you can see, basically the first order term is that V01 is simply the linear output, right. In this to get V02, what are we doing? We are, the input source is made 0, correct. So, we are de-energizing all the input sources, right, and in parallel with every nonlinear element or at the output or across every nonlinear element, you are injecting a nonlinear current, all right, which depends on the details of the nonlinearity of that element, as well as the voltage, in this case the voltage across that element in the linear network, all right. So, that therefore will cause the output here therefore will be a function of it's obviously a function of both V01, right, okay, and Vi, because the current through G1 basically in the original network, in the linear network, depends on V01 minus Vi, okay. So, the third order response, to find the third order response, you basically again you have the same network, linear network, right, but in parallel with the nonlinear element, you now inject a different set of currents. Basically you see all the third order currents that are being injected here, correct, and so on and so on, right. Most of the time, if you do, in a within quotes circuit that works properly, right, the second and third order distortion terms are often the most dominant, and therefore 2 iterations are good enough, right. And since this method basically within quotes is adding or injecting current, right, in parallel with every nonlinear element, right, this is called the method of current injection. All right, and so we will do a couple of examples perhaps in the next class, but one thing I would like to point out is that let us say the resistor only had, so let us do a simple example where the resistance had only odd order nonlinearity. So, this is basically Vi, this is C, this is Vo. So, this is Vo minus Vi plus G3 or G1 times Vo minus Vi plus G3 times Vo minus Vi the whole cube, all right. So, now there is no second order nonlinearity to talk about. So, what do you think? So there is one, of course, we can rewrite all the equations again, but based on what we have seen, right, what would we expect the output to look like? So, Vo of t must be of the form Z times V01 of t plus Z cube V03 of t, all right. Now, how do you find, finding V01 of t, what do?
Linear network will take only linear.
We will take only the linear network, so that is easy. So, we have Vi of t so this is G1 and this is V of 1, right. So, this is, remember, this is linear. Okay. The next step is to find Vo2 of t. Vo2 of t is 0, so V of 3 of t. What do?
We will take the G1
we will set Vi to 0. This is the capacitor. This is V0 of 3. This is G1. And this current is G1 times V0 of 1.
Depend on the V02.
Sorry, V02 is 0.
Yeah.
Correct. So, what do we need to put in?
Third order term
We only need to add the third order term. That is basically
G3.
G3 times V0 1 minus Vi the whole. Okay. And V out. So, once you know this and once you know this, well, the output can be written as put z equal to 1. So, V0 of t is nothing but V01 of t plus V03 of t plus higher order terms. But the hope is that, you know, if the resistance is only weakly nonlinear, the higher order terms can be neglected.